all led us to the general power rule for integration. One of the most common use subs involves quantities in the integrand that are raised to a power. Because the importance of this type of substitution, it's given a special name, the general power rule for integration. A proof of this rule follows directly from the simple power rule of integration together with theorem 413. So, if g is a differentiable function of x, then the antiderivative of g of x to the n power times g prime of x dx becomes our inner function raised up 1 power divided by the new power plus c. Remember, the g prime of x dx is sort of consumed in the process of taking the antiderivative. Equivalently, if u is equal to g of x, you have your u sub. You have u to some n times du. You just raise the power by 1, u to the n plus 1, divided by that new power plus c, as long as n does not equal -1, because that would result in a divide by 0 scenario. So let's play with a few of these. And let me clear a little space here. So, 3 times 3x minus 1 quantity to the 4th dx. Here is our inner function u. So the derivative of that would be 3 dx. We have a 3. We have a dx. So when we take the antiderivative, we're going to have our inner function, 3x minus 1. It was to the 4th. We raise it by 1. Divide by the new power 5, or multiply by the reciprocal 1/5. Add your constant. Ooh, this one's a little different. We have a numerator-denominator, and it looks like our inner function might be that denominator. So let's rewrite that with a negative exponent. We have our negative 4x is in the numerator. When we bring our denominator up, it's going to become 1 minus 2x squared to the negative 2 power dx. So inner function might be this. Let's check and derive it. That 1 would derive away. And then we're going to have negative 4x to the first. Ooh, and look at that. There's our negative 4x to the first dx. So there is our du, and our inner function is in the parentheses u. So when we take the antiderivative, the du is consumed in the process. We take our inner function, 1 minus 2x squared. We raise the power by 1. From -2, we move up to -1, and divide by the new power, divide by -1, or we could just put a negative out front, and we add our constant. And it is bad math manners to leave a negative exponent in our final solution. So this is over 1. We can drop that down to the denominator. We're going to have our negative out front. Our parentheses to the negative exponent move downstairs, and it becomes 1 minus 2x squared to the first power. And of course there's a 1 left up top, and we have our plus c, our arbitrary constant. And letter E, of course, we're not having fun unless there's a trig function to do. So here we have a cosquared sine x dx. And of course, we can move that exponent around. We have our cos of x quantity squared sine x dx. So if we think, is this my inner function? What is the derivative of cosine? It's negative sine. So we are going to have to tweak a negative in here. And to balance that, we'll put a negative out front. And let's write this in u notation. So we're going to have our negative antiderivative. This will be u squared. And then this becomes du. So take the antiderivative. Negative stays. That's going to become u to the 3rd divided by 3, or times a 3rd, plus our constant. And when we make our substitution back in, it's going to be 1/3 cosine to the 3rd of x plus c. And I forgot my negative. There's a negative here. We also got a negative out front. Negative 1/3 cos to the 3rd x plus c. Okay, now let's switch gears over to definite integrals, and we'll talk change of variables for those definite integrals. When we're using a u substitution with a definite integral, it's often convenient to determine the limits of integration for the variable u, rather than convert the antiderivative back to the variable x and evaluate those original limits. This change of variables is stated explicitly in this next theorem. The proof follows from theorem 413 combined with the fundamental theorem of calculus. And our theorem 415 states, if the function u equals g of x has a continuous derivative on our closed interval from a to b, and f is continuous on the range of g, then here's our definite integral from a to b of f of g of x times g prime of x dx. What we can do when we do our u sub, we have our f of u du. We can also change our upper and lower limits. We can take our lower limit a and plug it into the g function and get g of a. That's our new lower limit. And we can take the upper limit b and plug it into the g function and get g of b, our upper limit b. When we do this, we don't have to do our u substitution back. We don't have to substitute our original function back in and evaluate the limits that we were given. We can evaluate our new limits, leave everything in terms of u, which is usually much simpler. And let's try that here in example 8. Change of variables. Definite integral from 0 to 1 of x times quantity x squared plus 1 to the third dx. So I'm going to go out on a limb here and say our inner function is inside the parentheses, x squared plus 1. That means du, the derivative is 2x dx. Now let's see here, we have our definite integral from 0 to 1. I'll leave a little space here, x times our x squared plus 1 quantity to the third dx. So u is x squared plus 1. Here's our u, that's going to be u to the third. And we need a 2x dx for our du. We have an x dx, so we are missing the 2. And we have to balance that outside the integral with a 1/2. It's reciprocal. So let's see, now let's write this with the u substitution. We have our half out front, our definite integral, and we're going to leave those limits alone for now. I'm not going to write in the 0 and 1. So here is our inner function. That's going to be now come u to the third. And then we have our 2x dx, which becomes du. Now what we could do, if we wanted to, is leave our limits from 0 to 1, do the antiderivative, get 1/4 u to the fourth, and then plug back in our x squared plus 1 for u, and evaluate our upper and lower limits that way. But it is usually much easier to take those zeros and ones out of there. Our old limits were 0 and 1. That was the integration limits for our function in terms of x. We can find new upper and lower limits in terms of u. And all we do is take our u equals x squared plus 1, right here, our u sub, and we're going to plug the lower limit 0 in. This lower limit was 0. If I plug it in here for x, I get 0 squared plus 1, which is 1. And then I take my old upper limit 1 and plug it in for x. 1 squared is 1, plus 1 is 2. So now, after we do the integration, we don't have to switch back to x squared plus 1 and evaluate the old limits. We can just integrate with respect to u, plug in our new limits. And let's do it this way. These are the limits for x. So these limits, our upper limit was 1, our lower limit was 0. What we've done is found new limits. Limits for u. So let's take the antiderivative. We'll have the 1/2 out front. We raise our exponent 1 up to u to the fourth, and we divide by 4 or multiply by 1/4, and now our new limits for u are from 1 to 2. So we multiply our fractions and we get 1/8 u to the fourth from 1 to 2. Now we just apply the fundamental theorem. Take our upper limit 2 and plug it in. We're going to have 1/8 times 2 to the 4th power. And minus, we plug our 1 in, and we get 1 to the 4th is 1. So 2 to the 4th power. 2 times 2 is 4, times 2 is 8, times 2 is 16. So now we have 16 minus 1, which is 15. 15 times an eighth is 15/8. And that's our final answer. If we did not switch our limits of u, right here, after we had found our antiderivative, we would have converted this back with our u sub. This would be 1/8 quantity x squared plus 1 to the 4th power from 0 to 1, our old limits. And you can see that would be a little bit more complicated to run our upper and lower limits through it. It is usually much easier to leave it in terms of u and then run the old limits through that u function. Example 9, another change of variables. Now this one's a little different. Let's see, usually you'd think, okay, let me rewrite this. We got our definite integral from 1 to 5. That is x, and we have 2x minus 1 to the negative half power. Now you'd think, okay, I'm going to let u equal 2x minus 1, and then du would equal 2 dx. Now if we wanted to, we could continue down this path and it would work out just fine. We would get the correct answer, but it would take a few more steps than if we do it a slightly different way. So here, well, let me put that back. You know, we let our u substitution be the thing that is underneath the radical. And like I said, we've done that before, and it would work in this case just fine. But let me show you an alternate way that we have not quite seen yet. Let's let u equal the whole thing, radical sign and all. So let's let u equal the whole square root of 2x minus 1. And you'll see why this comes in handy maybe a little bit later in the problem. So let's square both sides. U squared equals, the squaring gets rid of the radical, 2x minus 1. And we are solving this for x. So we got to get the x alone. Let's add 1 to both sides. We're going to get u squared plus 1 equals 2x. And then we divide by 2. And I'm going to put my x on the left here. X equals u squared plus 1 over 2. And let's break those into separate fractions. X equals 1/2 u squared plus 1/2. And now let's take the derivative to see what's going to come up in our substitution. So if we derive this side, it's going to be dx equals, here the half and the square, the exponent that we bring down would cancel out. So we'd just be left with u to the first, and then the plus 1/2 would derive right off. And since we were deriving with respect to u, this would be dx du equals u, and then multiply both sides by du. So we have dx equals u times du. And you'll see why going this way is going to help simplify the problem as we get into the nitty-gritty of it. So let's start thinking about our u substitution, and we are going to find new upper and lower limits. So here our lower limit was 1. If we plug that into our u substitution, 2 times 1 is 2, minus 1 is 1, and it's under the radical. The square root of that is 1. So our lower limit doesn't change. Plug the upper limit 5 into our u sub. 2 times 5 is 10, minus 1 is 9. The square root of 9 is 3. So now we have a different upper limit of 3. And let's see here, our u substitution is this radical, and that was in the denominator. So we could sort of look at this as 1 over u, and then we have our x would sort of be out here. And we did solve for x right here, u squared plus 1 over 2. So I'm not going to put in x here, I'm going to put in u squared plus 1 over 2. U squared plus 1 all divided by 2. And then dx we can replace with u times du. So here is u du. And here's why doing it this route, letting the u sub be the entire radical, does make this a problem a little simpler. We have 1 over u times u. Those cancel out. So those are now gone. And we can drag this denominator, this 2, outside of the integral sign, and we will have 1/2 definite integral from 1 to 3 of u squared plus 1 du. And of course that would be in parentheses. So now we're ready to take the antiderivative. 1/2 raise the power by 1, divide by the new power, that's going to be u to the third times a third, plus we integrate 1, it becomes a u to the first. And our new lower and upper limits are from 1 to 3. Now you might be tempted here to pull that 1/3 out front, but you know that 1/3 is attached to the u to the third power. We don't have a 1/3 to factor out from just this lonely u over here, so we're going to just have to leave that as is. So we have 1/2. Run the upper limit 3 in. So we're going to have 1/3. 3 to the third is 27, and I'll put it over 1, plus 3. And then minus, run the lower limit 1 through, and that'll be 1/3 times 1, or just 1/3. And then plus 1. So our half is still out front. Here first, 1/3 times 27 over 1 is 9. 9 plus 3 is 12. Minus, here we have 1 1/3. 12 minus 1 1/3. So we want to, well, let's, how should we do this? We could distribute the 1/2. 1/2 times 12 is 6, minus, this would be 4/3, another way to look at it. 1 1/3 is 4/3. And we distribute that 1/2 to it, we would get 4 over 6, or 2/3. So we have 6 minus 2/3, which is 5 1/3. Or, as an improper fraction, 16/3. If you want to, you can go back and just let u equal what is under the radical, and you'd have u to the 1/2 power, and bring it up, make it u to the negative half power. Do the same process, you will have more steps. The evaluation of the integral will be a little more complicated, but you will get down to the same 16/3 answer. Geometrically, we can interpret this equation. We had our first, before the u sub, the definite integral from 1 to 5 of our function, and we said that was the same thing as the definite integral from 1 to 3 of u squared plus 1 over 2 du, to mean that the two different regions shown in these pictures have the same area. Here's our first function with the x's in it, and if we graphed it, it would look like this, and we're going from 1 to 5. So we can look at that, since it's completely positive, as the area under this curve. And then we look at our u substitution equation. It's part of a parabolic curve here, slight curve to that, and our limits were changed from 1 to 3. So here on the x-axis from 1 to 3, we're looking at this as the area under this curve. And geometrically, what we found is the areas are the same. This area is exactly the same as this area. Now let's talk a little bit about integrating and even and odd functions. Even with the change of variables, integration can be difficult. Occasionally, you can simplify the evaluation of a definite integral over an interval that is symmetric about the y-axis or about the origin by recognizing the integrand to be an even or an odd function. And here in Theorem 416, it says let f be integrable on the closed interval from -a to a. You know, it's symmetric. You know, we have our y-axis in the middle, and we are spread evenly around it. If f is an even function, then we can take from -a to a of our function and simplify it down to twice the integral from 0 to a of f of x dx. And I think it's easier to see down here graphically. Here is a downward opening parabola. It is symmetric around the y-axis. We want to integrate from negative a to positive a. And we can see that's hit right down the middle by the y-axis. So what this theorem says is we can start integrating at 0 and go to a and find this area, and we put a 2 out front and double it, since we are symmetric around the y-axis. If a function is odd, and we're integrating from negative a to a of a function that is an odd function, it's going to be 0. And if we look at this right here, we have a line downward sloped going through the origin. Remember, if it's positive, we can think about it as the area under a curve. But definite integrals can be positive, negative, or 0. And because odd functions are symmetric around the origin, if you want to think about it this way, this is above the x-axis. So you could say this is, for lack of a better term, positive area. And this here under the x-axis would be, you could say, negative area. And they would cancel each other out. If we look at just, the absolute value of the area, this little blue triangle that I just drew has the same area as this red triangle. One's positive, one's negative, so they would cancel out, and it would be equal to 0. If you recognize these even and odd functions, this could be a huge time saver on a test, especially the AP test. If it's on part where you could use your graphing calculator, if you're not familiar with the function and you notice that your upper and lower limits are the same, graph it. If it's partly above and below the x-axis and it is symmetric around the origin, the upper and lower limits are the same, you're going to have a definite integral value of 0. And let's see what's going on here in example 10. We have an odd function. We're evaluating from negative half pi to positive half pi. That right there should get the wheels in the brain turning that maybe something's going on here as an even or an odd function. I might be able to make this as 2 times the definite integral from 0 to a half pi of the same function. Or I might be able to just look at it, recognize what's going on, and say, oh, this is going to be equal to 0. And as a little refresher back from pre-calc, let's refresh what even and odd are. If we have f of negative x, and that is exactly equal to, sort of like we pull the negative out front, the negative f of x, this is an odd function. And if we have f of negative x is the same thing as f of x, that is an even function. Sort of like this negative didn't really matter. Maybe when you're thinking, the unit circle. Here at positive 1/4 pi, this is positive 1/4. Our x values are square root of 2 over 2. Our y value is square root of 2 over 2. When we look at the negative one, this would be negative 1/4 pi. We have a point here where our x value is still positive, square root of 2 over 2. And this is negative square root of 2 over 2. Remember, the y values are the sign values. So it doesn't matter. It does matter. Sine of 1/4 pi is positive square root of 2 over 2. Sine of negative pi is negative square root of 2 over 2. But if we look at the cosine values, here the cosine of 1/4 pi is positive root 2 over 2. The cosine value of negative 1/4 pi is also the square root of 2 over 2. So let's look at this function. Our function is f of x equals sine to the third of x cos x plus sine x cos x. Let's find out what f of negative x is. F of negative x. So I'm going to replace all my x's with negative x's. Negative x. Cos of negative x plus sine of negative x times cos of negative x. Now sine is an odd function. So if I'm doing the f of negative x, I can sort of pull the negative out front, and that's completely legal. So here sine of negative x is the same thing as the negative sine to the third of x. Cosine is an even function, so cos of negative x and cos of x are exactly the same. So that's just going to stay as a cos of x. Here again, sign is odd, so this negative will come out front and overpower this plus sign in between the terms. So that becomes a negative sine of x. Cosine is even, so the cos of negative x and the cos of x are exactly the same. So, what do we see here? Is this the same thing as negative f of x? Is this function even or odd? Could I put a negative in here, and does this negative get pulled out in front? Well, we took our first term and we negated it. This was plus our second term and we negated it. So we do have an odd function. Negative f of x is the same thing as f of negative x. So we do have an odd function. And by our theorem, if we have an odd function and we're integrating from a negative value to its positive counterpart, we know it's going to be 0. So therefore, by theorem 516, or in this, is it 416? And this is 416, the chapters are one off. This is by theorem 416. This integral, I'm not going to recopy the whole thing, but this is equal to 0. If you are on the AP test or any other exam and you do have access to your TI-89, it is much easier to see graphically. If you punch the original function into the calculator, you'll see a function that is symmetric around the origin, so we know it's odd. This is sort of positive up here. Because this is below the x-axis, it's negative. Since we are integrating from negative half pi to the same positive counterpart, those are going to wash each other out, and the definite integral will have a value of 0. And that's the end of section 5.5, integration by substitution.